Welcome. I'm Ennemcien. 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 You can view my channel by typing Ennemcien in Google or YouTube. Thank you. Let me invite your concentration to a fundamental aspect of nature. Not a single system welcomes change of any kind from its natural state. In dynamics, this unfriendly behavior we call by the name inertia in our rectilinear motion. When we deal with rotation, we refer moment of inertia. In the branch of strength of materials, this fundamental property we call by the name elasticity. In electrodynamics, there are several instances where this property is visible. For example, if you try to increase the strength or decrease the strength of current, or if you try to change the direction of current in a coil, the coil itself will oppose any type of change. This property is here we call by the name self-induction. Suppose there are two coils placed close to each other, and if you try to change current in one of them, the other coil, the nearby or neighboring coil, won't like it. It will oppose. And this behavior or this tie between these two coils we call by the name mutual induction. In human society, in our society, you can see this behavior, reluctance to any type of change. We may call it by the name social inertia. That's it. Now we come to our topic, that is dynamics of spring. And I restrict my discussion to helical springs. See this figure. This is a helical spring supported at a rigid support. Original or natural length of the spring is L. Suppose we apply a force at the free end of the spring, Fa. The applied force is Fa. So as to stress this spring, now the length of the spring increases to L plus X, or the extension of the spring is X. Now a restoring force will develop within the spring that will try to recover the original length of the spring. That's a natural tendency, as we have discussed just a few moments ago. Now, the restoring force, we denote it as Fr. See, the increase in length of the spring or extension of the spring is X vertically down in the direction of the applied force. But the restoring force Fr is vertically up. So Fr is always opposite in direction to the extension of the spring. Likewise, suppose the applied force Fa compresses the spring by the same amount x. Now x is in the upward direction. Now the length of the spring is reduced to L minus x, and the restoring force now tends to elongate the spring to its original length. So Fr is down, x is up, Fr is down. Here x is down, Fr is up. So here the speciality is the restoring force Fr is always directed opposite to the extension or compression. Now there is a simple relationship between x and the restoring force. This simple relationship we call it as Hooke's law of the spring. The Hooke's law, according to this law, Fr is proportional to minus of x. The negative sign simply suggests that Fr is opposite in direction to the extension or compression x of the spring. Or Fr equals minus a constant k into x. This is the basic dynamic equation of a spring. A soaring force Fr equals minus kx. This k is a constant of the spring. We call it as stiffness of the spring. Stiffness or spring constant or force constant. Spring constant, stiffness, or simply constant of the spring. There are several names. So the basic equation, dynamics equation for a spring is Fr, a soaring force Fr equals minus kx. Now we will discuss the dynamics of spring in detail in the next posting. Okay, thank you.